In 1913, Niels Bohr proposed a new theory that explained the spectral lines which couldn't be explained by Rutherford's planetary model. Now, Bohr's model works perfectly for the hydrogen atom. He assumed that the hydrogen atom had a single proton in the nucleus and there was an electron that was orbiting around this nucleus in a perfect circular orbit. He assumed that the electron's orbit would only occur at certain radii, as shown down here in this picture. These electron orbits were often called electron energy levels. He reasoned that when the electron was moving in this perfect circular orbit, it would not radiate energy, and that its internal motion was due to the internal structure of the atom. It would only radiate energy when the electron would jump from one energy level to another energy level. He stated that the electron is only allowed to be in one of these set of discrete allowed orbits, or energy states. These energy states were often called, once again, energy levels. While the electron is in one of these orbits, or states, or energy levels, remember that the electron doesn't radiate energy. It only emits energy when it makes a transition from one level to another level, from a higher energy level to a lower energy level. When the electron falls from one energy level to another energy level, it loses energy. And it loses this energy in the form of a photon. And the energy of this photon, which is equal to hf, is really equal to the energy difference between the higher energy level and the lower energy level. And that's written down here, down in the notes here. Whoops. Right there, the energy of the photon is equal to the energy of transition of the electron, which is the difference between the higher energy level to the lower energy level. So this is very key to your understanding in our problem solving. Now, the absorption of a photon is just the reverse. If a photon came in just with the right amount of energy to an electron, we could pop up this electron to a higher energy level. So again, electrons can absorb photons of light with energy that is exactly equal to that right amount of energy to raise the electron from a lower energy level to a higher energy level. Below in the notes, you'll see that Bohr also has a certain allowed radii, which is given by this formula, r sub n equals n squared times a sub 0. This a sub 0 is the smallest orbital radius, and that's what it is equal to for a hydrogen atom. Also, the allowed energies for a hydrogen atom, this is, by the way, for hydrogen, not for all atoms, is given by E sub n. N stands for the energy level, which is equal to negative 13.6 electron volts divided by n squared. And n can be 1, 2, 3, 4, etc. In general, for most atoms, you can say that E sub n, if you were to apply Bohr's model, is simply just the E sub 0 divided by n squared. You may also notice that there's a negative here. And the energy is negative since the energy of the atom with the electron being bound to the nucleus is less than the energy of the ionized atom. I'm not sure if you've learned about ionization in your chemistry class, but imagine if you have like an electron that's zipping along in space, just basically having kinetic energy, and it's not bound to the atom. It could be even at rest, but it's infinitely far away from the atom. And so it's not bound whatsoever to the atom, and we would say that atom is ionized. So how does one make an atom become ionized? Well, you have to give it enough energy so that you can get that electron to escape from being bound to the nucleus. This is a lot easier to discuss if we talk about energy level diagrams, which is on the next page in your notes. So let's talk about energy level diagrams. They're quite helpful in visualizing all of this. You see, for hydrogen, there's certain allowed energy levels or orbits for the electron. We like to usually talk about it as energy levels. So over here, down in your notes, right down here is a nice right in the lower right is an energy level diagram shown for hydrogen. So we have plotted on the y-axis total energy, and then we have different lines that show the different energy levels. The lowest energy level here at n equals 1 is called the ground state. You can see it occurs at negative 13.6. The way we got that for hydrogen, remember the general formula is E sub n equals negative 13.6 electron volts divided by n squared. So if we were to plug in n equals 1, we would get negative 13.6 electron volts divided by 1 squared, which is just really that. If you wanted to get the second energy level, you would be plugging in E sub 2 in here, so you would be negative 13.6 electron volts divided by 2 squared, and that would yield this result of negative 3.4 electron volts. And you can continue this on to infinity here. Now, all of the levels that are above the ground state, so n equals 2, 3, 4, 5, etc., are called the excited states. So if you were to give an electron enough energy so that it were to jump up to one of these higher levels, then we would say that it is in an excited state. Now just back to ionization for a moment. Imagine that you have an electron that is here at the ground state, and it's bound to the nucleus of the atom. But if you were to give it enough energy to completely free this electron from being bound to the nucleus, that amount of energy would be called the ionization energy. Essentially, you want to give enough energy so that you can bump up this electron all the way up to right in this area, right here where n is equal to infinity, and remove the electron from the atom. So for hydrogen, the ionization energy is 13.6 electron volts. If you were to add 13.6 electron volts to this electron, you would end up to a total energy of 0, and then that electron would be no longer bound to the atom, it would be free. With energy level diagrams, you should be able to calculate the energy or the wavelength of a photon that is emitted or absorbed in a transition between two energy levels. Let's take a look at some of the specified examples over here. Let's say you have an electron that is at the excited state of n equals 3. And let's consider all the different transitions you could have in which photons are emitted. So we have this electron at this higher energy state, and what are the different transitions it could make? Think about it. Draw the arrows that you think you could draw for this. Hopefully you can see that it could make a transition from n equals 3 to 2, or also it could make it state from n equals 3 all the way to n equals 1, the ground state. Furthermore, when this electron goes from the third state to the second state, it's still in an excited state there, and so hence the electron could make another transition from this second excited state down to the ground state here. To calculate the energy of the photon that is released, we need to find the energy difference between the two energy levels. So when the electron falls from a higher energy level to a lower energy level, it emits a photon, so that's my little photon here, and the energy is equal to the difference between the energies of these two levels. So that would be the difference between 3.4 electron volts and 1.5 electron volts, which is 1.89 electron volts if you take the difference of that. So that's one photon. And once you know that energy, you could calculate the wavelength of the frequency by using E equals hf or hc over lambda. So once you know that energy of 1.89 electron volts, then you could calculate its wavelength, for example. Now there are also other energies here. We have the energy of the photon that goes from the third state all the way down to the first state. So there's another photon here, E. This energy of this photon will be 12.09 electron volts, the difference between 1.5 electron volts and 13.6 electron volts. And lastly, we have also this excited state from 2 down to the ground state, and that would be another photon. And that would be the difference between 3.4 electrons and 13.6, which is 10.2 electron volts. All of these are emitted photons. Now, you could have an electron that is at ground state, or n equals 2, and it absorbs a photon just the right amount of energy so that it pops it up. Okay? Remember that when the photons are emitted, you're going to get the emission spectra that we talked about earlier, and when the photons are absorbed, you get the absorption spectra that we discussed earlier. So to recap of what you need to know when you solve problems with this is you need to be able to calculate wavelengths and energies when photons are emitted, when you have these transitions that are occurring from higher energy levels to lower energy levels, or vice versa, where you're getting both the emission and absorption spectra. You should also be able to calculate the ionization for removing that electron that's at the ground state all the way up to here to infinity. And furthermore, you should be able to construct energy level diagrams for some hypothetical atom. They may be able to give you sort of on the exam a bunch of different energy levels, and you have to draw your own energy level diagram and show these one-step or two-step transitions that we've been discussing. Well, the best way to get to enable yourself is to practice. So now go ahead and try the next two examples in the notes. And if you're struggling, use the videos to help you out.